Okay, good morning, everybody. Thank you for joining us today for an exclusive webinar on how ultrasonics can improve the processing of bioplastics. So I'm Idris from Impact Solutions, and I've got with me on the call webinar a few of my colleagues who are working on the SENTIO project, and I'll let them introduce themselves, starting with Ahmed.
Yeah, I am Ahmed Tayeb. I'm from Brunel Innovation Center. I'm leading the team of sensors and actuators, and I'm working for BIC for more than 7 years now, with a focus on collaborative projects that deal with mainly the use of power ultrasound to improve manufacturing processes, but also on some projects that involve electronic developments, some agri-tech and biomedical solutions.
Thanks, Ahmed. Over to McLaren.
Hello, hi, I'm Bruce McLaren, Managing Director of McLaren Plastics. We're a trade molder. We've been doing this since 1960, and we basically just mold on behalf of our customers. But over the last few years, we've done a few Innovate UK grants with the team at Impact Solutions. So that's how we got involved in this project, which has been a very, very interesting project, which we're about to show you all about.
Great. Thanks, Bruce. David, any extra words?
No, yeah, I'm sure as we go through the slides, yeah, I can jump in if there's anything. But yeah, McLaren Plastics, as Bruce said, we do everything from project concept through to design, manufacturing, tool manufacturing, and obviously processing in a broad range of polymers. And lately, yeah, exclusively in a lot of biopolymers that are just making it to the marketplace as we speak.
Great, thank you all. So a quick outline of today's webinar. We'll, after introducing ourselves, the presenters, the project, and our respective companies, we'll delve into the technical approach that we've developed during the project. We'll share some of our main findings through what the injection molding trials have shown and what the analysis on the bioplastic samples have shown as well. We'll also briefly cover what our next steps are now that this project is soon to be wrapped up, and we'll leave time at the end for a quick Q&A. So Impact Solutions is a testing center and R&D laboratory. So we're based just west of Edinburgh in Scotland. We primarily started in the polymer testing space, but we've recently expanded our research areas into industrial biotechnology, process intensification, battery science, and waste valorization. So as I mentioned earlier, we are a UCAS accredited laboratory. A lot of our strategy is based around trying to develop sustainable solutions for industry. And we tend to take a collaborative approach to working with our network of academic and industrial partners to develop those sustainable solutions. So we were established in 2002 as a spin out of BP Chemicals. And since then, we've grown our company to just under 50 people. And we've spun out three companies since then. So there's Impact Recycling, Reventis, and Cellmine. And we can tell you more about those via our contact details at the end of this email. I'll hand over to Brunel to give a quick introduction, or just to add to what was said earlier. Ahmed?
Brunel Innovation Center is a joint venture between TWI and Brunel University London. It's part of the Institute of Materials and Manufacturing of Brunel University, and we are based in TWI facilities in Cambridge. We run many collaborative projects. That's our main business, is research and collaborative projects in different fields, including power ultrasound, artificial intelligence, data science, agri-tech, biomedical devices. And this project, SENTIO, is related to our electronics and power electronics team developments.
Thanks, Ahmed. Bruce, any extra words on McLaren Plastics?
Yeah, I mean, it's just that, as mentioned earlier, we're a trade motor. We produce parts away from anything from a less than 1 gram all the way up to about 1.3 kg. Basically, any polymer you can think of, all the way from your commodity polymers like polyethylene, polyprop, polystyrene, to the engineering ones like ABS, nylon, acetyl, up to the real performance polymers like polysulfone. We work in many different markets like automotive, medical, packaging, agricultural, electronic point of sales, and we're also, over the last 5-6 years, also have customers now that already use biopolymers in mass volumes. So yeah, so we're a very diverse company.
Thanks, Bruce. So a quick overview of the SENTIO project. So our main aims are can be summarized into these 3 bullet points. So we are aiming to develop a process using ultrasound that overcomes the technical challenges of injection molding bioplastics. So to give a bit of background, injection molding is a thermal process to basically turn the pellets that you would produce via usually petrochemical-based feedstocks into a mold, which is the final form of the product. With the popularity of bioplastics, it meant that a lot of procedures had to be revised to account for the reduced thermal stability compared to petrochemical derived polymers. And when we're still seeing a slight lag in performance, I'd say, or in the processing of biopolymers compared to petrochem-based ones. So the team over at Brunel has come up with an innovative solution to try and overcome that. And it's through the introduction of ultrasonic subsystems in the injection molding machine that we're able to improve the performance of these bioplastics during the injection molding stage. So in 3 steps, we are essentially going to be designing and optimizing the ultrasonic subsystem. We'll be assessing the performance in existing injection molding machinery that McLaren have and characterize the effects this has on the biopolymer using our testing laboratory at Impact. And we'll be using the technical data gathered during the project to identify the target market areas and hopefully develop a business plan to take this forward. I'll hand over to Ahmed, who will give a quick rundown of the ultrasound subsystems. Thanks, Ahmed. Let me know when to do the next slide.
Yeah. Actually, Brunel Innovation Center has a long history and track record of developing power ultrasonic systems for many applications. We started with ship cleaning and then with wind turbine monopile cleaning as well, offshore wind turbines. We have had some experience with pipes unblocking in the food and nuclear industry. We used ultrasound for de-icing wind turbine blades. After that, we started using ultrasound for manufacturing processes, where we introduced our power ultrasonic system generator and transducers into 3D printing of parts in small modular reactors in nuclear industry, and also for the 3D printing of plastic for laser welding. And now the idea came, why not to use the same technology for injection molding of plastics, where we are always using almost the same principle, is targeting some manufacturing processes where we have molten material that is solidifying, and injection molding is a very good candidate for this. This is what you can see here on the image is our most recent ultrasonic power generator. You can see the on top the ultrasonic the ultrasonic signal generator that feeds the required signal into the big box in the bottom with the 8 transducers outputs. That's our very recent device. Each output here can generate up to 150 watts with a frequency ranging from 20 kilohertz to almost 250 kilohertz. These are the main specification, but we have also some flexibility on the waveform, the frequency sweep. The system has a lot of capabilities that can accommodate requests, special requests or specification from the end user. Yeah. Again, what you can see here in the left is the system with 8 outputs. In the right is a smaller version with only 4 outputs, but it's just scale up. As you can see, every module that you can see in these boxes can drive 2 transducers. In the right one, we have 2 times 2. In the other one, in the left one, we have 4 times 2, but it's exactly the same technology. The only difference here will be in the power supply board, which obviously for the left one has to produce more power. But it's flexible, modular, adjustable, and upgradable. That's what we can claim, and it can be extended up to 32 channels. Yeah, we don't want to take you through many electronics complications, but this is the assembling diagram of the unit with the 2 modules times 2 that makes 4 outputs, and you can see here it's a simplified assembly of the signal generator board, the power distribution, and the amplifier modules. Yeah, next slide, please. Yeah, we are using an important device here, which is the heatsink and the cooling fan, as the transistors get quickly very hot, and they will need some cooling. And yeah, this is also what we can see here. Yeah, these are it has 2 amplifiers, which means two transducer output. This is one model. Also, from a signal generator point of view, we have the flexibility to drive 2 different power generator. Well, what you can see, the TX1 and TX2 are the outputs where we compile the signal in the STM32 data board, and then we send it to the power generator. But in this system as well, we have the possibility to listen to the transducer and get some input through RX1 and 2. This is in case we need to make some closed loop system. And to sometimes what it happens, it didn't happen to us in this specific application, but what it happens is we can see some frequency and impedance shift in the transducer, and we will need to be able to track that and change the frequency instantly. And this is why we need some input for our signal generator. It is already equipped with these input. In case we need, we see a drop in the performance and we want to introduce the closed loop, it's our system is ready for that. Yeah, and that's the same photo. Yeah. Next one, please. Yeah, this is the power distribution board that gets the input voltage through center tapped transformer and gives us the plus minus 75 volts DC that is required. As you all can guess, we will need to get the AC power from mains and then transform it to DC voltage in order to be able to create the waveform that we need through the ultrasonic power generator. And this board plays a crucial role in producing the DC voltage. Yeah, next slide, please. As you can see here, we see our system connected to a few Langevin transducers that are up to 120 watts. And we made some performance tests, and we tried to check the reliability of our system and how long it can keep the same performance while running at maximum power. Yeah. From SENTIO project perspective now, we started using some plastic in our labs before moving to McLaren facilities. We made some checks to see how we can get high temperature using the ultrasonic friction. We used for this trial we used an industrial off-the-shelf transducer, and we got some plastic from McLaren, and we ran our tests using a thermal camera to check how far we can go in producing the heat. As Idris explained in the beginning, the aim in this project was to use ultrasonic power on two sides. The first side is to create cavitation in the molten plastic, and the second one is to assist the heating generation and to reduce the use of conventional heaters, and also to reduce the excessive and useless heating of bioplastic that might create some degradation in the properties. And with ultrasound, there is potential to make some localized heating of the plastic that is being prepared to be injected in the next injection cycle. Yeah, next slide, please. Yeah,
I can.
This was. Yeah. You can carry on with that. This was the Brunel stuff that was installed in McLaren plastics. Yeah, you can carry on with this, Bruce. Yeah,
no worries. So it was difficult to try and retrofit Brunel's equipment into an existing mold, because obviously an existing mold, there's a lot going inside, like the feed system, where the ejector pins are, etc. So the decision at the very beginning of the project was to quickly make a new tool in-house, but with the provision of space where possible to be able to adjust and add in all Brunel's equipment. So I don't know if you can make it out there, but it was actually a golf tee mold that we ended up using because that we manufactured because we wanted all the parts that were made through the trials to be able to be used after everything had finished, rather than just doing like a standard test plaque or something like that. So you can see here the mold and the start of the trials was the SENTIO, the Brunel probe attached to the side. So yeah, and preliminary what we did we did all the trials at the very initial stage in polyprop, just we got a baseline. And then so the next slide please, Idris. And then this is just some technical drawings of the mold that we made and being able to show the provisions, how we're going to attach the horns, etc., onto the mold. Next slide. And there, as you can see, the image down at the bottom on the left-hand side, we had two different sweep transducers that worked at different hertz. But as you can see, I don't know if you can make it out in the technical drawing, but what we were doing is we're trying to get those in the sprue as close to the part as possible. And then in conjunction with Brunel, my colleague David, who's on the call as well, they went through a series of trials, both with the ultrasonic switched on and off and just measuring the different influences that it had. So I don't know if David has anything he wants to add in at this stage.
The only thing is we ended up putting the 6mm horn into a manifold system that had cartridge heaters to heat up the manifold block to a minimum temperature, and then we used the ultrasonics that was with the horn that was in the melt flow to obviously agitate that melt flow and react to the plastic. That's the only thing really. So that's what you see in the view from CAD, is just a sectional view of the manifold system with the transducers in place.
And what's very interesting by this is we know from experience, because we have been using biopolymers for a few years, is how tricky they can be to process. So this is why this Innovate UK research project really appealed to us, because as I said at the beginning, we do have some biopolymer projects in mass production, and anything that we can do to give us a better process window will be very beneficial. And then again, so we started off with the golf tee molds on the left-hand side, but then during the project, it was decided to make a spiral flow tool as well, just to really help with the analysis. And because what we're also starting to see is if we either had the ultrasonics on or off, we could create a short molding. But then if we switch them up the other way around, we then had a complete molding. So we were seeing a difference between having the ultrasonics off and on. So the spiral mold on the right that we made as well, that really helped with that analysis, and the results that we submitted into Brunel would impact. So yeah. Next slide, please. Yeah, and then that's just one of our injection molding machines with all the equipment. The team at Brunel very kindly lent us to be able to control their equipment. So yeah, so yeah, that's what's going on there, and that's what we helped to do the trials with. And then at the beginning of the project, we always wanted to use polyprop just as a control. It's a known material. We know how it's going to work. And then through conversations with the rest of the guys on the grant, we chose these materials to trial with. So Evic Ecovia, I think it's how you pronounce it. That's like a PBAT/PLA. Solinatra is a PLA as well, but it's been modified in such a way that it doesn't need industrial composting. It's better for home composting and things like that. So we're very interested to see that, because that's quite a new biopolymer to market. Arbor foam is basically wood in a very, very simple term, and PBOH. We did trials both with cold water and hot water PBOH. Probably one of the most common uses of PBOH is that kind of very, very thin film that goes around your dishwasher tablets and things like that. But it's getting used in more and more applications at the moment. But it is moisture sensitive. So, and all of them, yeah, they're not quite as easy to process as a good old polyprop. So yeah, but it was very, very interesting. So yeah. Next slide. Oh, I think this is over to Idris now.
Yes, I can take over the reins. Thanks, Bruce. Thanks, Ahmed. Yeah, so as Bruce mentioned, we basically picked out these polymers to have a control and a range of different biopolymers. We kind of took a broad approach to defining what a biopolymer is. We've kind of mixed and matched some that are petrochemical derived but are biodegradable. We've also picked some that are bio-based but don't degrade as easily. So the Ecovio, like Bruce said, is a PBAT PLA blend. And I think because of the ratios that they use, it can count as home compostable. So in terms of assessing the performance of these biopolymers, so we took the Gulf teas that Bruce and the rest of his team manufactured with different parameters on the ultrasonic subsystem. And we were quite interested to see how that thermal journey that the polymer has gone through from pellet to mold has affected its properties, and more interestingly, whether it's had an impact on its biodegradability, because we're quite interested to see if we can exploit the ultrasonic subsystem to essentially control the rate of biodegradation. And I've just got some data earlier this week which addresses that. So in terms of how we think these chemical properties are linked to the ultrasound, so as Ahmed mentioned, the working assumption is that the ultrasonic waves induce local areas of high heat, and what that does is it creates an overall reduction in viscosity, and we're hoping that that means we can process the polymer at a lower temperature than needed. But we reckon that the ultrasound is leading to a decrease in the glass transition temperature, denoted here in TG. And what the glass transition is temperature is it tells you at what point does your polymer go from the amorphous region into the crystalline region. So a decrease in the TG value corresponds to a decrease in the crystallization. And what that means is it means that the polymer essentially becomes a bit more porous for water and anything in water. So in this case, bacteria and enzymes that can induce biodegradation. So we think that the reduction if we can measure the difference in TG, then we can start to look at how that influences the biodegradation at the end. So here's a quick overlay of a PGA analysis done on the PBAT polymer. So when we were monitoring the TG, which would be the peak temperature here, we noticed that it wasn't it wasn't changing as much as we thought it would. So and for us, it wasn't really good news or bad news because it was good news in the sense that the thermomechanical properties of the polymer are quite well preserved. And it means that McLaren could run their operations at a reduced temperature, but still offer something that matches the performance of a non-ultrasound made component. But we did, but we did notice that with the bio-based polymers that degrade more readily. So the PVOH, for example, that's a readily biodegradable polymer. We found that we managed to record a reduction in glass transition temperature of 5 degrees, which is significant but not meaningful for us. For the other polymers, so for the polypropylene, it's had no effect. For the Ecovio, it's had minimal effect. There was a 1-2 degree drop, but the most apparent drop in TG was in the PVOH. So we thought it's a good opportunity to check out how the PVOH exposed to different ultrasonic parameters and what effect that has on the biodegradation rate. So what we've done is we've taken the Gulf teas and we've run them through the OECD 301F test. So what that involves is taking your solid sample, so in this case the Gulf teas. I wish I had. I've got a nope. That's not a Gulf tea. It's another injection molded part. But essentially, we grind up the molded component into a powder, and we put a known quantity of that powder in a flask that contains activated sludge, and we connect that to a respirometer that can measure the CO2 over time. And using some equations which link up the CO2 production and the composition of the polymer, we're able to then work out what the biodegradation rate on day 28. So for a polymer or a prototype to pass the OECD 301F, it needs to show that it has degraded above 60%. So the results are quite interesting. So for a standard operation where no ultrasound was used, neither at the manifold or later on, we get a biodegradation rate of 77. When the manifold ultrasound was turned on and the ultrasonic sweep was also turned on, we noticed that the biodegradation rate dropped to 50%. So in this case, this one would have failed the OECD test. We did a further 2 tests. So the first two samples were done at 190 degrees, and the second 2 were done at 170. And you can see that for a similar ultrasonic parameter, so for the same parameters, we're increasing the sweep from 20 to 40 kilohertz. We've managed to bump up the biodegradation rate back to 61%. We do plan to repeat these. These were done in triplicate, but we want to get a lot more data on this because we're quite interested to see if there's specific parameters or specific locations of the ultrasound that are causing this change in biodegradation. But we're quite optimistic that this will lead to a future project where we can develop tunable biodegradable products. So in terms of next steps for the analysis on our end, so I mentioned earlier that the TG was a good indicator of biodegradability, but as you've seen from the graphs, we can't really notice anything meaningful. So we're going to start looking at other analysis that we can do on our polymers. Namely, we're going to do a GPC analysis, and what that does is it gives us the molecular weight distribution. So that's how varied are your polymer chains within a sample in terms of the chain length. So a reduction in molecular weight generally means that a material is more biodegradable because it's easier for a bacteria to take it into its cell, degrade it into CO2 and water, and then spit it back out. The other thing we're quite interested to look at is the OIT, which is oxidation induction time, and that essentially gives us a nice number to pinpoint what the thermal degradation has been throughout a polymer's thermal history. So we're expecting that the ultrasound-induced components have a higher thermal degradability, but we were surprised with the TGA results, so we might be surprised with the results from the OIT as well. So that brings us to the end of the webinar just now. Thank you very much for your attention. I've left the contact details here on this slide if you'd like to reach out to any of our companies. I think this is a good time to move to the Q&A section. Yeah, Sean, do you have any questions for us in the chat or anything you'd like us to cover that you might have missed maybe earlier on?
No, thank you. No questions from me at all. Much appreciated.
Great, thank you very much. Well, the meeting has been recorded, so I'll stop the recording soon and share a link on our LinkedIn and Eventbrite pages.
That's great. Thank you very much for your time. Much appreciated. All the best now.
Thank you for coming. All right, thank you guys, and see you next time.
Thank you.
Okay, thank you.
See you. Bye.
Bye-bye.